Okay, here we are on page 4, and notice what we're going to do now, combinations. Everything that we've been doing up to this point has been building to combinations. We've slowly been building up formulas on arrangements and orderings, and now we're going to be combinations, or sometimes the C people use it to stand for choosing. So here, an example. On the previous page, when we did number 17, how many four-person presidencies can you make from a club of 27? We started out with, oh, there are 4 people like this, and we did 27, 26, 25, 24. And we had the quick formula was 27 factorial over 23 factorial because we cut off those other 23 positions we weren't interested in. Well, now instead of a presidency, these 4 people are indistinguishable. So the orders that we have already counted up have counted up too many of them, and now we need to go back to how many distinguishable things, which means each of those 4 people in a presidency, when we turn them into a committee, they're indistinguishable. So we now need to divide by how many different ways they can mess themselves up. And in this case, how many different ways can 4 people mess themselves up? 4 factorial. So it gets to look just like this, and it turns out to be, hey, wait a second, I recognize that. And yes, we did many of them that turned out to be that these 2 numbers that were indistinguishable, non-committee people and committee people, were in previous exercises. Well, this is a formula. It's so common that it's often given its own notation. In choose R. So pick R things out of N, a group of size of R out of N things, and this is the formula. You'll notice we have both the N minus R and the R factorial. This one is cutting off what we don't want, and this one is how many different ways the people we do want can mess themselves up such that they are indistinguishable, and that's how many groups we have. So we will put this in, but we will often use just like this, 27 choose 4, which you'll see on the calculator. So I'm going to punch this in the first time 2 different ways. So we're going to write 27 factorial divided by 23 factorial 4 factorial equals, and we get 17,550. 17750. And that is the answer, but because it happens so often and we've built this up and constructed this formula, we will say it all the time. We're going to pick 4 members out of 27. Here's our formula, and this is how we do it on the calculator. 27. When we go to math, notice when we're over here in probability, what this one is, NCR. That is the most common one used with probabilities. So NCR 4. And notice it does all of that. It accounts for the fact that we are now doing groups. And this is the biggest thing. When you are dealing with groups, the other page, permutations, dealt with arrangements or orderings. We are dealing with groups of people or groups of numbers and not worrying about the order in which it happens. So, with no further ado, we can now zip through these kind of fast, because how many ways can we have 5 players of an 11-player basketball team attend study hall? Now notice in study hall, it's not a roster with a center and a forward and a passing guard and all that. It's a group of 5. So this is going to be 11 choose 5. Can be written like that, or 11 choose 5. Plug that into the calculator. 11 math probability in choose R 5, and it's going to plug in 11 factorial over 6 factorial 5 factorial. 11 choose 5 is indeed 462. Okay, number 37. How many 7-card hands can be dealt from a 52-card deck? And notice we're not giving it to individual students. This is a 7-card hand which you can shuffle around, and we're talking about 7-card groups. So this is going to be 52 choose 7, written also like 52 choose 7, and it's going to use this formula. So that is going to equal, let's plug it in, 52 choose 7 is a great big number. Let's see if I can write that all out. 13378 4560. Wow, that's how many 7-card hands could be given. All right, how many different groups of 4 letters can I get from a set of alphabet magnets? So if you have 26 alphabet magnets and you're getting groups, notice it's groups, not words this time, not orderings. So it is 26 choose 4. which is going to be 26 choose 4, which is 14,950. And it becomes very easy. You don't have to rethink through the whole problem. If it's a group of 4 out of 26, this is your answer. That's how many different ways you can get 4 out of 26. Number 39. How many committees of size 6 can be taken from a class of 14? 14, choose 6. And we know that it's a committee, it's a group, so we're not doing permutations, and we just plug it into the calculator. 14, choose 6 is 3003. And again, this is 14 factorial over 8 factorial, 6 factorial. You should note, I'm going to bring up just something really quick, that 14 choose 6 and 14 choose 8 are the same number because these 6 and 8 would switch places. 26 choose 4 and 26 choose 22 would give you the same number. 11 choose 5 and 11 choose 6 would give you the same exact number. And at first that's surprising until you realize that picking a 4-person committee from 27 members is the same way as picking 23 non-committee members. So 23, 27, choose 23, these numbers have to be the exact same because the way you can pick committees of 4, is the same as picking a committee of 23 or a non-committee of 23. So let's keep going. We have 21 and we want to get 14 pencils, just a group of 14. So 21 choose 14. It's not a fraction. That's 21 choose 14 equals, plug it into the calculator, and we get 116,280. Great. So that's combinations. When you have a group, jump through all the thinking through it. And if you need to, rewatch this one right up here to see how we got this formula. But once you've got it, use it. And we'll show you how handy it is and why it's so valuable to do it. In this case, it says how many different sandwiches can be made with the following choices if we choose 1 kind of bread, but 2 of everything else. So we're going to have bread, cheese, meat, veggies, sauces. We get 3 kinds of bread. But now on this, with the cheeses, just like we did way early on, we know we're picking 5 cheeses, but we get 2 of them. And it doesn't matter which order, so this one is going to be 5 choose 2. Now notice how quickly we did that. We said, how many different ways can I pick 2 out of 5 cheeses? And that's exactly what this formula means. For meats, we're picking 2 out of 4. So that's 4 choose 2. We're picking 2 out of 6. 6 choose 2. And for the veggies, we're picking 2 veggies out of 8. Now, if we decided that, we're going to do order on them, then we'd have to think through stuff. But if it's just groups, all the thinking has been accomplished here, and we'd have to do each one of these individually. This one is, you can punch that in a calculator and it's 10. You can punch this in a calculator and it's 6. This one is 15, and this one is 28. So we actually are taking 3 times 10 times 6 times 15 times 28. Now you can punch those in your calculators yourself, but I'm going to assume you have already done that. 3 times 10 times 6 times 15 times 28. Enter, and it turns out that we can make 75,600 different sandwiches, getting 2 of each of the different kinds of condiments. All right, number 42. How many different ways are there to get a full house? That's 3 of a kind and 2 of a kind when getting a 5-card hand from a deck of cards. Oh my word. So let's think about this. Normally you could do just 52 choose 5, and that's how many different hands you have. So that's how you do probability. So let's see how many different ways there are to get a full house. Now notice when you do that, you could get 3 of a kind of, say, jacks and 2 of a kinds of, say, 8s, or 3 of a kinds of 8s and 2 of a kind of jacks. Notice that order matters when we pick this. So this is 13 different suits for the 3 of a kind and 12 for the 2 of a kind. Now let's look at this. For each one of them, let's say jacks, 8s, once you pick one of these, the jacks, you have 4 jacks and you need 3 of them. So that's 4 choose 3. How many different ways can you get 3 out of 4 things? Eights, how many different ways can you get 2 out of 4 things? So once you pick your jacks and eights, this is how many different ways you can do it. So let's times this up. 4 choose 3 is 4, and 4 choose 2 is 6. So that's 24 different ways. So each one of these, 13 times 12, 156, has 24 different ways. So it's actually this times this is 24 times the number of different orderings of the jacks and eights. So we get 24 times 156 equals, and now we punch that in, 24 times 156, and we get 3744. Ooh, let's try another one like that. Hey, 43. How many different ways are there of getting 4 of a kind when getting a 5-card hand from a 52-card deck? So let's try it with what we know. You can have, again, jacks getting 4 of a kind, and then the 8s being the other card, or the 9s or the 10s or the 11s or the 12s, or you could have the 8s getting that. Wow, so you could have 8s and jacks again. So order matters if you get the 4 of a kind here and the 1 of a kind there. So this is going to be, again, 13 times 12 on how you pick which kinds of cards you have. So let's do it over here. Once you pick this, you have to get 4 out of 4 jacks, which only happens, 4 choose 4 is 1. And then you get 4 choose 1 of the other kind of card. Yeah. So this is 1 times 4 is 4. So we get 4 times 13 times 12, 156, equals, and that's going to be 624. Okay, now let's do 3 of a kind. These are kind of tricky. So we could have a jack, an 8, and a 7, where this is the 3 of a kind, and that's a random card, and that's a random card. Okay, so let's pick this. So the number of different ways we could get this guy is 13. Then these guys are interchangeable, so we don't do 12 and 11 because it doesn't matter which order we get them. So it's really a 12 choose 2 for the other 2 kinds of cards. So this is a different way we can pick which cards we get a 3 of a kind with. And now with the jack, you've got to pick 3 out of 4 cards, 4 choose 3, and then once you pick this one, you've got 4 choose 1 and 4 choose 1. Okay, so let's multiply that out. 4 choose 3 is 4 times 4 times 4, that's 64. So 64 times, and then 13 times 12 choose 2. 12 choose 2 is 66. 13 times 66. So this equals, let's plug that in the calculator, 64 times 13 times 66 equals 54,912. Number 45. How many different ways are there to get 2 pair in a 5-card hand? All right, so let's look at it. 2 pair, that means you could get a pair of jacks and a pair of 8s, and then 1 odd duck card over here that could be like a 6 or something like that, and that would get a 5-card hand. Well, notice this. How many different ways can you establish which cards you get to pick? And that would be 13 choose 2. It's not 13 times 12 because if you change order, it's different. So it's, of these guys, it's 13 choose 2. And then over here, you have, once you've used up 2 cards, you now have 11 choose 1 different options over there. Okay, so that's how many different ways you can pick which card you have. And once you choose which card you have, you've got a 4 choose 2 way, how many different ways you can get those jacks, 4 choose 2 on how many different ways you can get that card, and 4 choose 1 on how many different ways you can get those 6s in there. So this becomes 6 times 6 times 4. 6 times 6 times 4 is 144. And so we're going to take this guy, which is 13, choose 2, which is 78 times 11 is 858 times 144, and that equals 123,552. And finally, we're going to go out of a standard 52 card deck. We're going to go and do a 8 cards are dealt from a 52 card deck. So we've got to get a 3 of a kind, a 4 of a kind, and then notice we've got 1 card left over that can be anything it wants to. So let's do this. 3 of a kind, a 4 of a kind, and this. So you can get 13 different cards to be your 3 of a kind, 12 then to be your 4 of a kind, and 11 to be your 1 of a kind. So there's a permutation and ordering, because if you have different cards for this, so that's like having the jacks and then the 8s and then the 6s. And if you change those around, then it will be a different set. So how many different ways can I get 3 jacks? That's 4, choose 3. How many different ways can I get 4 8s? Well, 4, choose 4. That only happens one way. And how many different ways can I get 1 6? That's 4, choose 1. So we're going to take 4, choose 3, which is 6, times 1 times 4 gives us 24. And then times 13 times 12 times 11. So 24 times 13 times 12 times 11 equals, so this is if you were dealt 8 cards, this is how many different ways you could get a 3 of a kind, a 4 of a kind, and a 1 of a kind. Kind of like you're playing skip bow or something there. So 24 times 13 times 12 times 11. That is 41,184. All right, these are really pretty intense questions, and you may have to review those a couple of times to see where we pulled out these numbers and where we pulled out those numbers. All right, good luck with